Okay, this is a pre-video for section 2.6 on inequalities. We're going to go over some basic things that would have been covered in 023 and Math 100, just to get us a good start on talking about inequalities, especially compound inequalities, and then absolute value inequalities and polynomial and rational inequalities over the next week. So an inequality is a statement that two quantities or expression are not equal. So most of us know the greater than or less than, greater than or equal to, less than or equal to. You could also have a not equal to symbol. That actually is an inequality symbol, but it's not one of the ones we're concerned with in this section. So one of the biggest things that I find students struggle with is making sure you can read the symbol from left to right. Most of us have learned the alligator thing at some point in our life, and we want to make sure that if you read a sentence or a statement, you know if you're supposed to say less than or greater than. So when you're looking at the symbol, if you see the point first from left to right, then that means you are dealing with a less than symbol. If you're looking at the symbol and you see the mouth or the opening first, you're reading that as greater than. That's actually a really important skill to make sure you graph things on the number line appropriately. So consider the inequality 2x plus 3 is greater than 11, where x is the variable. Now, if you didn't know what the solution set was, or if you didn't know how to solve it, you could try testing different x's to see if they come out as true or false. So for example, in this table, they put in 3, which 2 times 3 would be 6, plus 3 more would be 9, and 9 is not greater than 11, so that would be a false statement. You could try 4, and that would make 8 plus 3, which is 11. 11 does not stand greater than 11. If that had been an equal to sign, we would have been okay, but is not greater than itself, so that's also false. 5 gives us 2 times 5 is 10, plus 3 is 13. 13 is greater than 11, so this is true, and then 6 is also true. So what we find out is that there's not just one solution. There's going to be a subset or group of the number line that's going to work and satisfy the inequality. So if a true statement is obtained when you plug in a number for the x, then we know that that number specifically is a solution to the inequality. To solve an actual inequality means to find all of its solutions. So two inequalities are equivalent if they have exactly the same solutions, just like two equations were equivalent if they had the same solution set. Most inequalities will have an infinite number of solutions. So look at this. This is what we call a compound inequality because you see multiple inequality symbols. And this actually says 2 is less than x, but x is less than 5. So every number on the number line between 2 and 5, which I've shaded down here, would be a solution to this compound inequality. And this is an open interval because there's no equal to bars. We don't actually include 2 and 5 in our answer set. Now when you write your answer set like this here, 2 to 5 with a parentheses, a lot of people think that looks like an ordered pair. But when talking about inequalities or domain, it's not an ordered pair. It's what we call an interval of solutions or values that we can plug into something. And this is called interval notation. Interval notation is always a starting value to an ending value. Okay? And it always goes from least to greatest, and the parentheses or brackets, which we'll see one in a minute that has brackets, tells us whether or not the endpoints are included. So this is the graph of 2 to 5 with open intervals. You see a parentheses and a parentheses. A lot of times you might have remembered this from 023, possibly with open circle, and then shade in the middle. There's nothing wrong with that. The reason we do the parentheses is so that it translates to interval notation a little bit better. And if you draw out the number line and you sketch and shade what is considered to be the solutions, that's called sketching the graph of the interval. And remember, 2 and 5 we said are the endpoints. Now, if you had 2 is less than or equal to x, which is less than or equal to 5, that then is a closed interval. And notice we use brackets for the equal to. And when we shade that, we also use the brackets. This will translate back to other math classes you may have had where you might remember that as a closed circle. You can also have what are called half open and half closed intervals. Some books call them half open, some call them half closed. They mean the same thing. If it's half open, that means one side is open and the other side's closed. Same situation. You could also have an infinite interval. Remember that infinity, the sign is like a figure 8 on its side. There's two different infinities. There's a positive infinity to the right, and there will be a negative infinity to the left. So this chart right here, you'll just want to look at this. This is just all the different possibilities for what your solution could look like when you're solving, and then how would that translate onto a graph. So as we answer these, we'll probably see, okay, I always usually talk you through the interval notation, and then we always talk through the graph as well. So that means we're ready to do a couple examples to set the stage for our class session next week. So example 1 says express the inequality as an interval and then sketch its graph. So the first one is x is less than or equal to 5. That's why it's important for us to be able to read that statement. So if I wanted to graph that, I always draw a little number line, because I usually do the graph first because the interval comes very easily from the graph. I need to find 5, so if you put a 0 here, 5 would be somewhere over here. If you want to put all the tick marks, you can. I'm not going to require you to do that because graphing is important, but normally we give you the number line on the test, so you don't have to make up your own spaces. So if we want to go less than or equal to, first of all, equal to makes me think, oh, that's an endpoint that's included, so we need to use a bracket. And notice I'm opening my bracket towards the left side because this is a less than. If it was a greater than, I would make my bracket open towards the right side. I always open it to the side that I'm going to shade. And then I shade all the way to the negative infinity. So this is negative infinity over here. And then this all, and if you want to see it better, I can even do like a color shading. We're saying all of this is shaded, okay? In interval notation, you always read from left to right. So negative infinity to 5, and 5 has a bracket. Now, infinity is always open. It does not ever get a bracket on it. It's always going to be a parentheses or a parentheses on the other side, depending on which infinity you're going to. The way I think of that or explain it is that infinity is not really a number per se, it's more of an idea. So you can't really close on an idea. You can close on an actual number or include an actual number. There's always going to be something smaller or something bigger than the two infinities because it continually gets bigger or smaller forever. Now this next one is x is greater than negative 3. So let's graph that first. So if 0 is here, negative 3 is going to be somewhere over here. And this is not equal to, so we're going to use a parentheses, and then we're going to shade to the right since this time it is greater than. Smaller goes left, greater than goes right. Because number lines are always ordered from least to greatest. Okay, so this would be negative 3 parentheses, and this time we're going to positive infinity to the right. And remember parentheses on it as well. Okay, these next three are dealing with the compound type inequalities where the x is trapped in the middle. That means that we have a boundary. So we're not going to be going to positive or negative infinity at all. We're just going to be going between these two endpoints. So for this first one, here's 0, here's negative 3. Since there's more numbers, I'm actually spacing them out this time. I need a bracket on negative 3 and a parentheses on 5. Notice I'm opening them towards each other because this says x is trapped in between. So then my interval notation would be bracket negative 3 to 5 parentheses. Okay, negative 3 to negative 1. Here's negative 1, 2, negative 3. And these are both open, so that's going to be 2 parentheses. And we're shading in between because x is in between both. So that would be negative 3 to negative 1, close parentheses on both sides. This one is a little bit different. Notice that this goes negative 3 is greater than or equal to x, which is greater than negative 5. They have written this from greatest to least. We don't like to graph that way. So if you want to switch the order, it's allowed as long as you flip all of the inequalities. And not only that, make sure they have the right inequality next to them. This negative 5 is supposed to have something pointing towards it, and it does not have an equal to sign. This one is open to the negative 3, and it does have an equal to sign. So that's just making sure you flip the whole thing around. And then it says the same thing. So here is 0, -1, 2, -3, -4, -5. And this is, again, brackets, because on one of them, on the -3, there's brackets because of the equal to bar. On the -5, it's a parentheses. Oop, and that deleted. There we go. So then we shade in the middle. So this would be -5 to -3 with a bracket on the -3 because of the equal to. Okay, so that's a good review of interval notation and graphing inequalities. This next one says, write this as an inequality. So it says express the interval. So they've already given us the interval. They want us to write something like this. X is either between two numbers or X is greater or less than something. Anytime you have two numbers, you're going to be doing an in-between case. So it just needs to be from least to greatest. So 0, and then there'll be an X, and then there'll be a 4, and then we just need to make sure we get the right symbols. So this would be a less than or equal to. Now, because this is saying that X is bigger than all of the zeros. See how the opening is to the X. And then X is going to be stopped right before we get to 4. So X is less than 4. Something to note is that in an inequality that's compound like this, all of the points should be heading in the same direction. They're either both going towards the left or they're both going towards the right. They should never be both opening towards X. That would not make sense. Okay, and then for this one, this is 3, and then our X, and then our 7. And these are both going to be just less thans. So X is bigger than the 3, but X is less than the 7. For this next one, we get -3 to infinity, so that means we're getting bigger forever. So that would be X is just greater than -3, not equal to, because this does not have a bracket on it. And then X is from -infinity up to 2 means we're always getting smaller than 2. So X is less than or equal to 2 because we do have the bracket. All right, and then the final thing on the pre-video is just a very simple solve an inequality. We will pick up here in class and actually start doing the compound ones, the absolute values, and then we'll start polynomial inequalities. So the methods for solving inequalities are similar to those that we use for equations, which means that we can use a lot of the same properties. There's just one that gives us a little bit of trouble. So if you have an inequality, you can add something to both sides. That's one of our properties. That's actually property 2. Property 1 is the transitive property. It says if A is less than B and B is less than C, then A, the original, has to be less than C. So that's just transitive. So 2 is less than 5, 5 is less than 9. Obviously, then 2 has to be less than 9. But you can add to both sides or subtract to both sides without any issues. We can multiply both sides by something and divide by something, but the only problem is if you multiply by something that is negative or divide by something that is negative, it flips the inequality. Let me show you why. So if I have 2 is less than 3, okay? Right now that's true. 2 is less than 3. If you were to divide that by -1 though, so we know that, I'm going to write this again, 2 less than 3 is true. Notice I'm dividing by a negative. If I didn't change anything, this is now false. So -2 is not less than -3, because if you think about the number line, -2 is farther to the right, because here's -1 and here's 0. So if you divide or multiply by a negative, right here is when I did that, you have to also flip the sign. So we go from being a less than to a greater than. So that's where that property comes from. It makes sure that the statement is still true. All right. And I wrote that here. It is important to remember that multiplying or dividing both sides of an inequality by a negative real number reverses the inequality sign. That was property 4. Okay, so one of my examples is missing, so I'm just going to add it in real quick. Must have got cut out from my edit. I believe this is example 3. So what we want to do is solve an inequality. And I'm looking just to make that bold real quick. It's not what I want. There we go, home. Okay, so we want to solve the inequality. And let's write our answer in interval notation. Okay, and this is going to be the interval or the equation that we're going to do. So I believe I had 2x plus 17 is less than 3x minus 4. Okay, so if we wanted to solve this, this is just like solving an equation. We need to make sure that we isolate the x's on one side and then make sure that everything else is on the other side, just like we would solve for x in any other situation. You could move the 2x over. That is one way to approach these. Or you can move the 3x over by subtracting. That will create a negative in front of your x. Just because of graphing, I usually try to get my x on the left side. This is the only time I would ever think about maybe having a negative x instead of trying for a positive x. I'll show you both ways, because even if you decide to do moving the x to the right, when you go to graph or write your answer, you still might want to flip things around. So if I do this by moving this way, I'm going to move the x's to the left just to make it read better. So if I want to do that, I would subtract over the 3x. That would be just negative 4 on this side. That would give me negative x plus 17 is less than negative 4. I would then subtract over my 17, which makes this negative 21. And then I would have to divide by a negative because we're not allowed to have that negative 1 in front of that x. So when I divide by the negative, notice that that makes this x is greater than positive 21. Because negative times, or divided by negative, is positive, and because I divided by a negative, I needed to flip it. So that would be if I moved it to the left, if I liked keeping the x on the left side. And I do like that because it reads better. This says x is greater than 21. If you chose to keep x positive, which you can't always do, it just depends on the numbers involved, but a lot of people would have chosen to move it over and keep it positive. Notice that means we would have subtracted the 2x over, and this becomes just x minus 4 over here. You add over the 4, you get 21 is less than x. That's not as easy for people to get interval notation from sometimes. I think our brains just don't read it the correct way, or to graph from. So at this point, you would flip it around. And if you flip everything, you do have to flip the inequality, because this still needs to open to the x. So either way, it gives me the same solution. I just wanted to show you that attacking it a certain way might make it easier for you. So just so you can see that. So that's my solution. That's in just what we call like a statement. It's the inequality statement. For the answer that they wanted, we want to write this in interval notation. So we're getting bigger than 21, but we're not equal to 21. So 21 to positive infinity. And that's it for our pre-video. So I'll see you guys in class next week.